Hello everyone, and welcome to this video. This is the second half of the past paper, paper 1 from January 2013. And in this video, we will be doing the last 50 marks of the paper, which is the final 4 questions. So, of course, as opposed to the first video where there were 7 questions over 50 marks, these are only 4 questions. The questions will be longer and more in depth. And one thing I want to make clear is that oftentimes questions in newer papers will have each part lead into one another, unlike the older papers here, which are mostly separate parts, in that the A, B, and C sections of a question would not necessarily tie into one another. But in newer papers, you really have to watch out for that, because if they ask you to evaluate something, there's a good chance you'll need to use it in the next part. Alright, so the first question, question 8, is a trigonometry question. Solve for 0 is less than theta is less than pi. Okay, so given that it's in pi, I'm going to guess it's in radians. So theta will be in radians. So I'm just going to switch the calculator over here. Anyway, so firstly it says 5 sine theta minus 1 is equal to 0. Alright, so 8a, 5 sine theta minus 1 is equal to 0, and that means that 5 sine theta is going to be equal to 1. Alright, let's zoom in a bit. 5 sine theta will be equal to 1, or in this case, sine theta is 1 over 5 for 0 is less than or equal to theta is less than or equal to pi. Alright, so here we can just use the theta is the inverse sine, meaning that we're undoing the sine function's action on theta to get the angle we want. So sine negative 1 over 5. You punch this into the calculator, you'll get 0.201 radians. And the thing is, the thing you need to watch out for, if you look at the unit circle and you notice the range from 0 to pi, at any given level of sine theta, except for, of course, 1 at the very top, there will be 2 values of theta which work, and one will be, let's call the first one theta, then in this case the second one will be pi minus theta. So it will be 0.201 radians and pi minus 0.201. And in this case, because we've not fully evaluated that one yet, so pi minus 0.201,357 ... Alright. So if we actually evaluate this on the calculator, shift pi minus ans, meaning the previous answer, or 0.201,357, that exact number that we got from the calculation on the calculator, it will give us 2.940. So the question is asking us to give each solution to 3 significant figures. So since this is above 1, 3 significant figures would just be 2.94. So in this case it's 0.201 radians and 2.94 radians. Now in this case, I don't think you will need to give the answer explicitly in radians, because it's not talking about a geometric shape, and this is just what you've ended up with, because normally the functions are considered by default to have radians as the input when you're using them in a mathematical equation like this, rather than a situation where geometry is involved. So we can box that as our answer. Right, secondly, tan 2 theta plus pi over 3 is equal to 0.4. Okay, like I detailed in one of the videos in my Learn Trigonometry, the first thing to do here is evaluate what actual interval of the angle in the brackets we are looking for. So if 0 is less than or equal to theta is less than or equal to pi, what about 2 theta plus pi over 3? So first we're going to add pi over 6 to both sides, so pi over 6 must be less than theta plus pi over 6 must be less than or equal to 7 pi over 6. And if we multiply everything by 2, we should get the 2 theta plus pi over 3. So pi over 3 must be less than or equal to 2 theta plus pi over 3 must be less than or equal to 7 pi over 3. Now you may be wondering why I'm actually doing this, and the thing is, when we take the inverse tangent of 0.4, as it is obvious to do so, we will get this angle, and we want to know which values of this angle will give us a value of theta that's within the range. But we don't want to accidentally ignore any values of this angle inside the trig function that could lead to a possible solution for theta, because the range for this will be much larger than the range for theta itself. So that's why we're evaluating it something like this here. So you would say, for example, let u be 2 theta plus pi over 3. Then you would get tan u is equal to 0.4. And also this would lead to the detail that pi over 3 would be less than or equal to u would be less than or equal to 7 pi over 3. And of course, this being u, it would just be tan u is 0.4. And obviously the next step is to use the inverse tangent, so u would be equal to tan negative 1, 0.4 for this interval. And so if we put that into the calculator here, we will get our first angle 0.380. But if my suspicion is correct, okay, so pi is around 3, and pi over 3 is going to be around 1. So I immediately know that 0.38 is not going to fly as our value of u. So the value of a tangent will be equal every pi radians. Like if you look at the unit circle, it's equal here after a half turn, which is pi radians. Then it's equal again after a half turn, which is pi radians, because the tangent is the gradient of the line coming out of theta. So we can add pi to the answer to get another possible value. So u could be 3.5220 ... And if we add pi to this one more time, we get 6.663 ... Okay, so if pi is just over 3.14-ish, then 2 pi would be like something like 6.3, and to get another 1/3 of pi on top would bring it to solid 7.3, so I think we can pretty confidently say that 6.663 will be in the range of values of u that we want. So u is equal to that, or it could be equal to 6.6636 ... And then to get to our actual value of theta, since we have u is 2 theta plus pi over 3, well, theta must be equal to u minus pi over 3 over 2, because first you subtract pi over 3 from both sides, and then you divide both sides by 2 to get just theta on one side. So applying this to both sides will get us, in this case, minus pi over 3, then divided by 2. This will get us, for our first answer, so answer minus pi over 3 divided by 2 is 2.808, or for 6.6636 that will give us to 2.808 something something. And for the previous answer, we start at 3.52209 and so on. Then we subtract pi over 3 and divide both sides by 2, and we get 1.2374, so on so on. And it's asking us to solve the solution to 3 significant figures. So to 3 significant figures, we round these figures we got here. And by the way, I'm using more decimal places than necessary to make sure that it's accurate, because I don't want to accidentally get an error from inaccuracy that would cause me to round in the wrong direction. So it would be 1.24. And here will be 2.81, because 3 significant figures, it would be the first digit before the decimal and then 2 more digits afterwards. So that's our answer to B. And finally, question C, 4 sine squared theta minus 7 cos theta is 2. Alright, I think we can use the trig identity that sine squared theta plus cos squared theta equals 1 here. And we're probably going to be treating this like a quadratic equation, since I see a squared, a linear term, and a constant. So 4 sine squared theta, okay, so firstly I'm going to write our identity is that sine squared theta plus cos squared theta is equal to 1. And in this case, this means that cos squared theta is equal to 1 minus sine squared theta. Or actually what we're looking for is that sine squared theta, because that's the one which is squared, if I'm not mistaken. Yeah, sine squared theta is going to be equal to 1 minus cos squared theta, and so 4 sine squared theta is equal to 4 minus 4 cos squared theta, multiplying both sides by 4 here. So making this substitution, we get the case in this equation that 4 minus 4 sine squared theta, or 4 minus 4 cos squared theta minus 7 cos theta is 2. And because this is a quadratic equation, what I'm going to do is move everything into the power order and move the constant term to the right hand side by subtracting 2 from both sides. And we'll finally get minus 4 cos squared theta minus 7 cos theta plus 2 is equal to 0. And because I do not like it for the first coefficient to be a negative, because it makes it a lot more difficult and painstaking to work with, I'm going to multiply both sides of the equation by -1. So 4 cos squared theta, and then minus 7 times -1 is positive 7 cos theta, and then plus 2 times -1, of course, minus 2 is 0. So what we can do here is we can try to factor it out, because now it's just a quadratic equation that we're solving for cosine theta. So if you remember how to do factor by grouping, we can say that, for example, our AB is going to be equal to minus 2 times 4, because we're looking for 2 numbers to split this plus 7 into. So it will be minus 8, and our A plus B, meaning the sum of the 2 numbers that are multiplying to minus 8, is going to be positive 7. And immediately I can see that our A and B is going to be positive 8 and minus 1, because these will add up to positive 7 and they'll multiply to negative 8. Therefore, we get that this equation is equivalent to being equivalent to 4 cos squared theta. I think I will put the plus 8 first. So plus 8 cos theta minus cos theta minus 2 equals 0, and factoring out the 4 cos theta here is equal to cos theta plus 2 minus cos theta plus 2, because this minus multiplies out to both of these to get this two terms over here. And this is equal to 0, and then we factor out this term cos theta plus 2. So we bring this outside, and it's cos theta plus 2 is equal to 4 cos theta minus 1. 4 cos theta plus 2 multiplied by 4 cos theta minus 1 is equal to 0. Now, because, at least with the real numbers, cosine theta will be part of the interval -1 to 1, therefore, cosine theta plus 2 being equal to 0 it cannot be true, because it would suggest that cos theta is -2, which is not possible with real numbers. So we would say that 4 cos theta minus 1 is 0, or cos theta is positive 1 over 4, and theta would be the inverse cosine of positive 1 over 4, which would be, looking at our calculator here again, 1.318, or in this case, well, I'm going to write it out first, and then we are rounding it to two significant figures. Alright, the thing is, with cosine and the interval from -pi to pi, you don't need to worry about multiple answers, because as you go around this half of the circle, you are going across the full range of cosine values from positive 1 here to -1 here, and there is no point where you are looking at two cosine values which are the same. If they were to be the same, they would have to be beneath the circle as well, which they are not. We are only looking at the top half, which would mean that every value of cos theta here would be unique from -1 to 1. Alright, so we boxed that as our answer, and I'll consider this question complete. Now, question 9 is a series question. I'm going to write the time down as 17 minutes 40. Alright, so this seems to be, again, an arithmetic series question rather than geometric, which makes me think there's going to be a geometric series question in the next paper. Yippee. Okay, so the sum Sn of the first n terms of an arithmetic series is given by n times 2n plus 3. The first term of the series is a. Show that a is 5. Okay, so firstly, it would be best to state the obvious here, the fact that the first term will be equal to the sum of the first one terms, because if you like think about the numbers involved in adding up just the first one term. It's just the first term by itself. So if you evaluate the sum of the first one terms, you get the first term, because there's nothing else added to it. Okay, so since the first term is equal to the sum of up to 1 terms, which is equal to, that means that the first term is equal to 1 times 2n, where n is 1, plus 3, which is equal to 2 plus 3, which is equal to 5. Therefore, a, the first term of the arithmetic series, is 5. So we've proven this by evaluating the sum of the first one terms. Okay, b, find the common difference of the series. Alright, so 9b, what we can do here, I think that I'll want to Yep, so I'm going to figure out the sum of the first two terms, and then take the first term away to find what the second term is, and then find the difference between T1 and T2 to get the common difference. Okay, so the sum to two terms is 2 times 2 plus 3. We're just using the formula they gave us, substituting 2 in for n, which is equal to 2 times 4 plus 3, or 2 times 7, which is 14. And the second term is equal to the sum of the first two terms minus the sum of the first one terms, which is 14 minus 5, which would be equal to 9. And finally, the common difference d, it will be equal to the second term minus the first term. Since we know this is an arithmetic series, it explicitly tells us here. So d is the second term minus the first term, as it is arithmetic series, which would be equal to T2 being 9 and T1 being 5, is 9 minus 5 is 4. Okay, so that's the common difference. Okay, find the 12th term of the series. Well, we know that for any particular arithmetic series, the nth term of the series is going to be a plus n minus 1 times d. That is the first term plus however many common differences you add on to get to that term. Like if you're looking for the 12th term like we are, you're adding 11 common differences on from your starting point at the first term. So term 12 would be a5 plus 12 minus 1 times the common difference 4, which would be 5 plus 11 times 4, or 5 plus 44. And the T12 would be 49. So we'll box that as our answer. And finally, given that 1 plus the sum to p plus 4 terms is equal to 2 times the sum to p terms, find the value of p. So the sum of terms formula, we're just going to use the one they've provided here. So let's see. Answering part D here. First, we'll find the expression for 2sp. Well, because we can just substitute n in for p, 2sp is going to be 2p times 2p plus 3. Okay, so that'd be pretty easy. So substituting p in for n, sum to p is going to be equal to 2 times the sum to p is going to be equal to 2 times p times 2p plus 3, because we're just substituting p into here and multiplying by 2, because 2sn would be 2 times this, right? And then substituting n in for p plus 4, we'd get the sum to p plus 4 will be equal to p plus 4 times 2 times p plus 4 plus 3. And if we expand that bracket out, we get p plus 4 times 2p plus 8 plus 3, and then the plus 8 and plus 3 will become the constant term plus 11, so p times 4 plus 2p plus 11. Or rather, p plus 4 times 2p plus 11. So next we're going to write this equation out and solve it, because it looks like it's just going to be a quadratic equation. So for 1 plus sp plus 4 to be equal to 2sp, so it's going to be 1 plus p plus 4 times 2p plus 11 is going to be 2p times 2p plus 3. We're going to expand both sides here, so 1 plus, well, first is 2p squared, and then plus 4 times 2p is plus 8p, plus 11 times p is plus 11p, and then plus 4 times plus 11 is plus 44. It's going to be equal to 2p times 2p is 4p squared, and then 2p times positive 3 is plus 6p. Or in this case, to write it out more neatly, we are going to put it in the power order. So 2p squared plus 8p plus 11p, so that's plus 19p, plus 44 plus 1, that's going to be plus 45, is equal to 4p squared plus 6p. And since this side has the larger p squared, we're going to be subtracting from this side to get our 0 on one side. So we subtract 2p squared, that's 2p squared, and then we subtract plus 19p, so plus 6p minus 19p is going to be negative 13p. And then plus 45, and subtract it, it's minus 45. Alright, so once we have this here, we have 0 on the left-hand side. And at this point we can factor by grouping. So, well, at least it looks like we can factor by grouping. That's what I suspect we'll have to do. So, yep, I can see what factors it's going to be. So AB is going to be minus 90, because it's 2 times minus 45. Then A plus B is going to be minus 13. And after sort of thinking about the factors of 90, I got onto 18 and 5. It's going to be positive 18 and minus 5 are the factors that we want here. And so if we split this negative 13 up into, or rather negative 18 and a positive 5, we'll get 2p squared minus 18p plus 5p minus 45 is equal to 0. So if we take out the 2p factor from here, 2p times p minus 9 plus 5 times p minus 9, because we're factoring out the 5 from here, is equal to 0. Or in this case, 2p plus 5 times p minus 9 will be equal to 0. So this gives us two solutions for p if it were a regular quadratic equation. But we know that since p is a series index, p must be an integer. Therefore, p cannot be, or the integers above 1. So p cannot be negative 5 over 2, as suggested by this factor. So that means p must be equal to 9 is our only answer for this. Alright, so we'll box that as our answer because we are setting this factor to 0. P minus 9 is 0, so p is positive 9. And I will consider question 9 complete. Alright, moving on to the next question. This looks like some alpha-beta black magic that we'll have to be doing. It's got a 7-part sub-question. It's a bit intimidating. I think we'll get through it just fine. So I'm going to write the time down as 28 minutes for question 10. Alright, so we've got a function here, fx. Actually, I'm going to drink some first. So fx is 2x squared minus 5x plus 1. The equation fx equals 0 has roots alpha and beta. Without solving the equation, find the value of alpha squared plus beta squared. Okay, when it says without solving the equation, you cannot solve the equation. Like, if you do, in any part of your answer, if you use elements from the quadratic formula and so on, it'll just be disqualified. Like, you won't get any marks. You can't do stuff relating to the discriminant and all that. I once tried to use the like 2 times the thing that comes after the plus or minus in the quadratic formula, apparently that counts as solving the equation, so don't do that. Just assume, for safety, that you are only allowed to use the values of alpha plus beta and the value of alpha beta in order to find your in order to find the answers that you're looking for. Alright, so firstly, it's telling us to find the value of alpha squared plus beta squared. Okay, this is quite the classic predicament that you will be presented with. It's important to realize that alpha squared plus beta squared is equal to alpha plus beta squared, and like alpha plus beta is something we're allowed to use, minus 2 alpha beta, because when you expand this out, it's this plus 2 alpha beta, so you subtract 2 alpha beta to compensate and you'll get this. So this is how you're able to get alpha squared plus beta squared from these two quantities. And of course, alpha plus beta, the sum of roots, is going to be your negative b over a, so it will be positive 5 over 2 in this case, because negative 5 is 5, and the coefficient a is 2. And alpha beta, the product of the roots is going to be c over a, or 1 over 2 in this case. And that means, after substituting, alpha squared plus beta squared will be alpha plus beta, or 5 over 2 squared, minus 2 times alpha beta, or 2 times 1 over 2. And this will be equal to 25 over 4 minus 1, or 21 over 4 is our final answer for alpha squared plus beta squared. Now, B, show that alpha to the power of 4 plus beta to the power of 4 is equal to 433 over 16. Alright, so it seems like we'd have to know the way to get to this sort of alpha 4 and beta 4, the power of 4, which is actually not something I've encountered before. Alright, so I think I've actually read something on the internet about this type of question before, the sum of a certain power of a quadratic equation's roots. So I think it might have something to do with, say for example, you have 2x squared minus 5x plus 1. So if you have 2 alpha squared minus 5 alpha plus 1 is equal to 0, and 2 beta squared minus 5 beta plus 1 is equal to 0, then you would know, for example, that if you multiplied this all by x squared with 0 on one side, the 0 would stay the same, and you'd get something like 2x to the 4 minus 5x cubed plus x squared is equal to 0. And the roots would still hold, basically, is what I'd say. Like 2 alpha to the 4 would be equal to 5 alpha to the 3 plus alpha squared. And you know what, it was an interesting proposal I saw on the internet, and like it would work with the other root as well, so this would not be a minus, in fact. It would be 5 beta cubed minus beta squared. So what I suspect is that if we add these up together, we would get on one side 2 alpha 4 plus 2 beta 4, which we'd be able to factorize this 2 out, and on the other side we'd get 5 alpha cubed plus beta cubed, which we know how to get normally, and minus alpha squared plus beta squared. then we'd be able to get alpha 4 plus beta 4. Alright, so let's try our hand at that actually, because this is a really interesting question. I hope that there's a easier way to do it, given that this is just 2 marks. But I feel like it's something that could work. And firstly, I see that this kind of looks similar to 21 squared. The only thing that's been taken away is the minus 1 over 2. So, or rather, what's been taken away would be the negative 1 over 2, I suspect. And in fact, this might not actually be the way to go about it, because I've just had the revelation that this is probably approached in the same way as we did this. So, right, one thing I'm going to try is the alpha squared plus beta squared squared, which would be equal to, of course, alpha to the 4th plus 2 alpha squared beta squared plus beta to the 4th. And the reason that I thought of this attempt is basically because the numbers here look very similar to this square. Like 21 squared is 441, 4 squared would be 16. Like this number, if you square it, it looks remarkably similar to this. So I suspect that it would have to do something like this number squared, right? So, and we see this 2 alpha squared beta squared. This could be expressed as 2 alpha beta squared, or 2 times a half squared, because like we know we're allowed to use this quantity alpha beta. So what I suspect is that we need to use our value here, square it, subtract 2 alpha beta to get our final answer. So this is an exciting train of thought we've jumped onto. Alpha to the 4 plus beta to the 4 is equal to alpha squared plus beta squared minus 2 alpha squared beta squared like this is squared as well. So it would be 21 over 4 squared minus 2 times 1 over 2 squared, which would be 441 over 16 minus 2 times a half squared, and a half squared is 1 over 4, so minus 2 times 1 over 4 is minus a half, and this of course would evaluate to 443 over 16. Nice! So we managed to prove it in a much more elegant way than I first thought we could. Alright, that is a good streak we're having here of successful figuring things out. Alright, so part C. Form a quadratic equation with integer coefficients which has roots alpha squared plus 1 over alpha squared and beta squared plus 1 over beta squared. Alright, the thing is, this qualifier, without solving the equation, it basically means we have to do this every part of the equation without solving the equation. So even part C, constructing a new equation, we have to do it without solving the equation. So what I'm going to do is I'm going to evaluate the sum of these and the product of these in order to figure out how we can actually make the coefficients we want. And then after we make those coefficients, regardless of it being an integer, then we'll convert it to being an integer by multiplying by the highest common factor of all the denominators of the fractions we have, if there are any fractions anyway. Alright, so let's take a crack at it. 10C. Let alpha 2 be alpha squared plus 1 over alpha squared, and beta 2 be beta squared plus 1 over beta squared. In other words, our 2 new roots for this equation. So our equation is going to be like a valid equation, that is like disregarding the integer requirement, would be x squared minus alpha 2 plus beta 2 x plus alpha 2 beta 2. And so this would be our b, and this would be our c. Or in fact, this whole thing would be negative b. That's what we're going for. Okay, so first we're gonna work out what alpha 2 plus beta 2 is in terms of alpha and beta, and we want to be finding a way to evaluate it legally, so to speak, with just the values of alpha plus beta and alpha beta that we are known to have. Alright, and I feel like alpha 4 plus beta 4 is going to come into play, given that like there's a 4 power difference between these, like alpha to the 2 and alpha to the negative 2. I feel like this identity is going to come into play somewhere, but we'll just see. So alpha 2 plus beta 2 is equal to alpha squared plus beta squared plus 1 over alpha squared plus 1 over beta squared. Alright, so we know what this is, but do we know what this is? Let's try and find out. This is equal to alpha squared plus beta squared. We're going to cross multiply this to get it into one single fraction. So multiplying both sides by multiplying both sides by alpha squared would get us actually, yeah, so both halves of this fraction, like the top part and the bottom part, we're going to multiply by beta squared, and both parts of this fraction we're going to multiply by alpha squared in order to get the one single fraction. So this will be beta squared over alpha squared beta squared plus alpha squared over alpha squared beta squared, which would be equal to alpha squared plus beta squared plus alpha squared plus beta squared over alpha squared beta squared. Wow, a lot of squares. Quite the arrangement we have here. So how can we evaluate this? We substitute, or we don't need to put the arrow there. We substitute the value of alpha squared plus beta squared being, what was our value? 21 over 4. And that alpha squared beta squared, we worked this out already. It was 1 over 2 squared, which is 1 over 4, if I'm not mistaken. And we get that this is equal to 21 over 4 plus 21 over 4 divided by 1 over 4. And these divided by 4's cancel out, so we're just left with 21 over 1, which is 21. So it's 21 plus 21 over 4. And this is 5 1/4. So this is equal to 26 1/4, or 105 divided by 4. So this is going to be our negative b over a of the equation. 105 over 4. Now I'm just going to double check that we're not dropping any negative signs here, because I feel like this is a danger when we've got so much calculation to do. Yep, we determined that this would be our negative b. Our 1 over 5 over 4 is a negative b over a, the sum of the roots. Secondly, let's try and find the product of the roots. So alpha 2 beta 2 is equal to alpha squared plus 1 over alpha squared multiplied by beta squared plus 1 over beta squared. Now, where does this go? So first we have alpha squared beta squared, which is equal to 1 over 4 plus 1 over alpha squared times beta squared, and alpha squared times 1 over beta squared. Oh man, this is going to be an ugly evaluation. Plus 1 over alpha squared plus 1 over beta squared. And of course this is 1 over 4, which is just a plus 4. So we are left with this ugly fraction in between that we want to evaluate again. So I think we'll have to do beta squared, multiply both sides of this by beta squared, multiply both sides of this by alpha squared to get, in fact, we are going to get the expression that I predicted would come up, which would be beta 4 plus alpha 4 over alpha squared beta squared. And that's how we get our fraction here. And of course, this is going to be 4 plus 1 over 4 is going to be 17 over 4. And then plus beta 4 plus alpha 4, we already found out is 443 over 16. Divided by alpha squared beta squared, which is 1 over 4. Of course, these cancel out. This is just a 4 instead of a 16. So it's 17 over 4 plus 443 over 4, which works out to, using my calculator here unashamedly, 460 over 4, or in this case 115, I think. Just double checking, 115, yep. So this is our sum of the roots. This is our C over A. So therefore, this leads to our equation being x squared, and then minus, what did we evaluate as the sum of the roots? Minus 1 over 5 over 4. X plus 115 is equal to 0. And we multiply everything by 4 to get rid of the denominator in the fraction, because it's asking for integer coefficients, which would give us 4x squared minus 105x plus 115 is equal to 0. Now if I do make a mistake, please comment if you find that I made a mistake, because again, this question is a lot of calculation, and we're 47 minutes in, so who knows what might happen. But the actual working should be sound, like my logic should be sound. Anyway, you can always check the mark scheme if you're just looking for an answer. That's not the purpose of this video, really. So I will consider question 10 to be done. We've boxed our answers, and like the reason I keep doing this is something you'll find that if you study math further, you'll end up doing this a lot just to make clear what your answer is, because you'll have so much working it'll be a bit ridiculous to go for more answers again. Alright, so we're moving on to this question, which looks like a graphing question, but it's too long to be just a graphing question because we had a long graphing question before. Alright, so there's calculus snuck in here as well. The last 12 marks is calculus. This is a 16-mark question. I'm going to write the time down as 48 minutes 20. Alright, so we've got this question here. Given that fx is x minus 1, x minus 3, x plus r, find the value of r, 1 mark. Okay, so this indicates to us pretty clearly that there's an easy way to go about doing this. And what I'm guessing is, since r is the constant term, and we know the constant term, 6, when we expand all these out, the constant term will be minus 1 times minus 3 times r. And this will get to positive 3r is equal to 6. And so r is probably going to be positive 2. So just need to write that out. The constant term is 6 is equal to minus 1 times minus 3 times plus r. Or 6 is equal to 3r, r is equal to 2. That's what we found out. Hence or otherwise, find the value of P and the value of Q. Alright, so I think at this point we can just expand and see what we get. So, given that R is 2, we know that Fx is going to be equal to x minus 1 times x minus 3 times x plus 2. And this is going to be equal to, first expanding these brackets, we get a x squared minus 4x plus 3 is minus 1 times x, and minus 3 times x is minus 4x, and minus 1 times minus 3 is positive 3 times x plus 2. And then we get x cubed plus, okay, so plus x cubed plus 2x squared minus 4x squared. Like, this is from multiplying this to the first one, and then we're multiplying this to the second one, then we're multiplying this to the third one. So minus 4x squared minus 8x, and then plus 3x plus 6. And we evaluate this all together to get x cubed minus 2x squared minus 5x plus 6. Therefore, once we know the full fx, we can say that p and q are going to be those two coefficients here. P is negative 2 and q is negative 5. And just to check that it's a plus p plus q, yep, so p is going to be negative 2, q is going to be negative 5. Alright, so figure 2 shows the curve C with the equation y is fx, which crosses the x-axis at the points with coordinates 3, 0 and 1, 0 at the point A. And at the point A, so A is the third point of crossing. The point B on C has the x-coordinate 2. Oh, this sentence doesn't end with a full stop, so I thought there would be more. Anyway, find an equation of the tangent to C at B. Alright, so it looks like we're going to be doing some differentiation. So if fx is equal to x cubed minus 2x squared minus 5x plus 6, then we know that the derivative of fx will be 3x squared minus 4x minus 5 plus 0, because this is a constant, and we're just using the power rule here to do this differentiation. So the m, like we're going to say the line is going to be y is mx plus c. M is going to be the differential of fx at 2, which will be 3 times 2 squared minus 4 times 2 minus 5, which will be 12 minus 8 minus 5, or negative 1. And we want to find out what the y-coordinate is at this point here, or we want to find out the coordinates of a point that passes through. So y for x is 2 is going to be equal to f of 2, which will be 2 cubed minus 2 times 2 squared minus 5 times 2 plus 6, or 8 minus 2 times 2 squared is 8, so these two cancel out, minus 10 plus 6, or this is just minus 4. So we know it passes, it's got a gradient of negative 1, and it passes through the point 2 comma minus 4. And that means where y minus 4 is equal to negative x plus c, or negative 2 plus c, or minus 4 is minus 2 plus c, and in this case c is minus 2, because we're adding 2 to both sides here. That means the tangent line, let's see if they've given us a name. Okay, so they haven't given us a name for the line. I'm just going to call it L. Leads us to being y is equal to negative x minus 2. That's our tangent line. Alright, so that was relatively easy. Show that the tangent at B passes through A. Okay, so I think we're going to have to find the point A and show that it works at B. And of course, A is going to be the root when x plus r is equal to 0. Therefore, x plus 2 will be 0, y will be 0, to make the whole equation 0, or the fact that x will be negative 2 and y will be 0. So if we sub x is negative 2, and y is equal to 0 into L, we will be demonstrating that 0 is equal to negative 2 minus 2, which is equal to plus 2 minus 2. And this equation will be true. Therefore, A lies on the tangent, which will be L. And finally, question E. Use calculus to find the area of the finite region bounded by C and the tangent at B. Oh my goodness. Okay, so at the moment it looks like the tangent is going to be this line here. Goodness me. So given that it's like turning away, I think that the tangent is going to just touch it at one point here, right? And it's not going to pass through the curve C again because the gradient is increasing here. And so in this case, the area we're looking for is just going to be this area here, and not any tiny bit after point B. It'll probably be like the integral from here to here of like integral of C minus our line L dx from A, which would be negative 2, to B, which would be positive 2. Or that's the values of x that we're concerned with anyway. So first we will say that the area is equal to the integral from negative 2 to 2, which is the two intersection points of C and B. So C dx minus the integral of negative 2 to 2 B dx. And that ultimately will give us our distance in between the two curves. We'll be adding up the infinite rectangles in between these two curves, between those 2 points. So this will be equal to the definite integral from negative 2 to 2 of C minus B dx, which will be equal to the definite integral of C, which is x cubed, or we've written it down here, x cubed minus 2x squared minus 5x plus 6. And then minus b, which would be minus x minus 2 dx. Or in this case it would be negative 2 x cubed minus 2x squared. Well, minus 5x minus x would be minus 4x. And then plus 6 minus 2 would be plus 6 plus 2, which would be 8. So this integral dx. And of course, using the power rule, this evaluates to 1 over 4 x to the 4, or actually this is in some certain bound. 1 over 4 x to the 4 minus 2x squared. That integrates to minus 2 over 3 x cubed. minus 2x squared plus 8x from negative 2 to 2. Alright, how do we deal with this? So, at the moment it looks like it'll be, since it's 1 over 4, or we'll first put our 2 bound, and then we'll see if there's any similarities we can cancel out here. So it'll be 1 over 4 times 2 to the 4, because like these two numbers are the same. There's got to be something that'll happen to make this calculation less complicated, right? So 1 over 4 2 to the 4 and minus 1 over 2 negative 2 to the 4, they might cancel each other out. So I'm going to write one on top of the other and see which terms cancel out. So minus 2 over 3 times 2 to the 3 minus 2 times 2 to the 2 plus 8 times 2. And from all of this, subtracting 1 over 4 times minus 2 to the power of 4 minus 2 over 3 times minus 2 to the power of 3, and so on and so forth. Alright, so minus 2 to the power of 4 and 2 to the power of 4 are equal because 4 is an even power. So that means these two terms cancel out, and the same for this even power, the squared, which means these two terms cancel out. So it'll be equal to minus 2 over 3 times 8 minus 2 over 3 times 8. So minus 16 over 3 minus 16 over 3, which would be these two terms. And then plus 8 times 2 plus, so this would be 16, 8 times 2, and then minus 16. Like, just to be clear, this is from this term, and this is from this term, which is the opposite. Like, it'll be the negative of this term. This is from this term, and this is the negative of that term over here, this term. And we will get to in fact, this is going to be minus positive 16 over 3, because minus 2 over 3 times minus 8 will be positive 16 over 3. So it's minus 32 over 3, plus 16 minus minus 16, so it's plus 32, or 32 minus 32 over 3 will be our area. And, well, this leaves us at an area of 64 over 3 unit squares. So we box that as our answer for part 11E, which is the final part of question 11. Right, so I don't really have any more tips to give for this question, just like because the limits were the negative of each other, there were some things that could be cancelled out. So that might be helpful information in the future. Anyway, thanks for watching.